Even if transmission is likely on average, there is always a chance that an infectious individual will not manage to transmit. You can think of this like a coin flip. Even if the probability of getting ahead when you flip a coin is high, say 90%, there is a real chance that any given flip will come up as a tail. Of course, if you flip lots of coins, you're pretty likely that about 90% of them are going to come up heads, even if you can't tell which ones exactly will do so. This is relevant to the establishment and persistence of transmission in populations, because each contact between an infectious and susceptible individual can either result in transmission or not, just like a coin can only come up heads or tails. For an infection to spread in a population, it is not necessary for all infected individuals to successfully transmit, so long as, on average, the number of new infections is greater than or equal to the number of old infections. For an infection to persist in a population, it is necessary for at least one infected individual to pass that infection onward. And if all the infected individuals in a population fail to transmit, then the infection will go locally extinct or fade out in that population. Again, returning to the coin flipping analogy, fade out occurs when all the coins come up tails. And intuitively, this is more likely to happen if you're only flipping a few coins and if the chance of getting ahead on each coin is low. From the standpoint of disease transmission, the number of possible coins that can be flipped is the number of contacts between infectious and susceptible individuals. And the chance of that contact resulting in transmission is dependent on the transmissibility of the pathogen itself. Following this line of reasoning, we might intuit that the number of infectious and susceptible individuals will scale with the population size. So larger populations will have more opportunities for transmission, that is, more coins to flip. Then, for any given pathogen, the probability of continuing to get at least one transmission event at any point in time should scale with the population size. And at some point, the population size should be large enough that transmission at any given time point is a virtual certainty. We refer to this population size as the critical community size. Formally, we can define the critical community size as the smallest population size for which any given infection does not go extinct. One of the most classic exhibitions of the critical community size has been the observation that measles infection, in the era preceding the development of measles vaccine, was always present in cities of greater than 300,000 to 500,000, but was frequently absent in smaller towns, and more frequently absent the smaller the town. Practically, this has important consequences for control. Effectively, in communities below the critical community size, infection would be expected to go extinct naturally due to the stochastic failure of chains of transmission. If infection persists in large communities, however, there is always the possibility of reintroduction. This pattern, large cities with persistent infection continually reinfecting small towns that experience local fade-out, was readily apparent in the pattern of measles epidemics in England and Wales prior to the development of the vaccine for measles. This led to a dramatic pattern of directional waves of infection spreading outward from large cities like London and Manchester, which were above the critical community size, to smaller towns in the countryside. Vaccination, by reducing the number of susceptibles, can reduce the effective community size in large cities, making local fade-out more likely and breaking the cycle of reintroduction to smaller towns. Now, the value of the critical community size will depend on both the characteristics of the population and the characteristics of the pathogen. For immunizing infections, once infection has spread through a population, a large proportion of the population may be immune due to prior exposure. And the more transmissible the infection, the higher the R0, the larger will be the proportion of the population that is immune, and the fewer infectious and susceptible individuals will be around. Thus, more transmissible infections are more likely to burn themselves out in all but the largest populations. Pathogens that induce a long infectious period are less likely to fade out as each infectious individual has more time to encounter a susceptible individual and successfully transmit infection. Many pathogens exhibit seasonally varying transmission rates, famously shown by the increase in childhood infection rates during school terms and the corresponding decrease during school holidays. For such infections, it is not the average number of infections that is critical to the probability of local extinction, but the depths of the troughs between epidemic peaks. It is at these points when the number of infectious individuals is at its lowest, and thus the probability that all of them will fail to transmit infection is at its highest. As an example of this, the critical community size for measles in Niger was estimated to be about 3 times higher, nearly 1.5 million people, than was classically observed in Europe. This was shown to occur because seasonal changes in urban population density due to agricultural practices result in very low incidence of infection and very low transmission rates during the rainy season, when many people are widely distributed on their individual farms. As a consequence, even in the largest cities in Niger, measles would frequently go locally extinct following outbreaks. This erratic pattern of outbreaks and local extinction is exacerbated by the high birth rate in Niger. Following local extinction, all the children born are not exposed to measles infection until the next outbreak, and given that some children won't be vaccinated, the population of susceptibles builds up over time. This buildup of susceptibles sets the stage for an increasingly big outbreak once measles is reintroduced from elsewhere. A big outbreak spreads fast, rapidly depleting the susceptible population, leading to a high likelihood of local extinction, thus continuing the boom and bust dynamics. These dynamics of local fade-out and transmission may also play a role in the establishment of an outbreak. Consider the first infectious individual in a susceptible population, and let P be the probability that infection goes extinct before it causes a major epidemic. That first individual can either recover from infection at a rate gamma, or can transmit infection at a rate beta. If transmission occurs, then there are 2 infected individuals who must fail to transmit if the infection is to go extinct. Thus, the probability of extinction P can be expressed as P equals the probability of the first individual recovering before transmission, plus the probability that the first individual transmits before recovering, times the probability that both infected individuals fail to transmit. With some algebra, we can then show that this can be expressed as the probability of extinction before a major epidemic is equal to the rate of recovery divided by the transmission rate, or 1 over R0. Thus, not only do pathogens with high R0 spread fast in populations, if they arrive, they are highly likely to result in an outbreak in the first place.